My name is Mohammad Adil Inam. So to start off, audit logs maintain a history of events that occur during system executions. Since these logs record the interactions between different subjects and objects on the operating system, they are an invaluable forensic tool for threat investigations. To simplify investigations, analysts can parse these audit logs into data provenance graphs, and upon an indicator of compromise, an analyst can query these data provenance graphs in hopes to identify the root cause of an attack. So while audit logs are an invaluable forensic tool, for certain attack classes, they might not contain enough information for complete attack reconstruction. So in other words, what happens when key attack behaviors can't be accurately explained through existing audit logs? So to look further into this, let us consider the case of configuration-based attacks. So configuration-based attacks are attacks resulting from improperly configured softwares. Our studies on the CVEs reported in the past decade showed that configuration-based vulnerabilities constitute about 4% of total reports in the past decade, and we have seen a rising trend in recent years. Moreover, apart from their prevalence, these attacks can also have dire consequences. So OWASP ranked security misconfigurations as one of the primary reasons for data breaches. And for example, in July 2019, a configuration-based vulnerability in Capital One's firewall leaked the credit card information of more than 100 million customers. And there are many more examples like that. So given the prevalence and security implications of configuration-based attacks, it is important to understand and analyze whether these attacks can be effectively investigated using existing audit infrastructures. So to explore this, let us consider a case study in which an attacker exploits the configuration of different systems. We consider a simple scenario where a company makes use of Exponent CMS, a web content management system, to manage its website. Moreover, this CMS is connected to a Redis database at the back end. The configuration state of the Exponent CMS can be updated on disk, whereas the configuration state of Redis can be updated both in disk and on memory. So the attacker in this case performs a series of attacks. First, the attacker exploits an underlying vulnerability in Exponent CMS and overwrites the configuration file and injects code into the configuration file of the CMS. In this case, the configuration state of the CMS is updated on disk. The attacker then executes arbitrary system commands and exploits another vulnerability within Redis to dynamically update its configuration in memory and eventually gain privilege escalation, which leads to the leakage of the database. So in this case, the configuration state of Redis is updated on memory. So after realizing the database compromise, an analyst then begins investigations by making use of system-level logs. These system-level logs collect logs traces at a system call granularity. First, the analyst discovers the shell that resulted from privilege escalation in the first attack, and from there, the analyst issues back and forward trace queries in hopes to identify the root cause of an attack. Root cause identification is important here because it can expose any system vulnerabilities and also prevent these attacks from happening in the future. However, root cause identification in the case of system logs presents various challenges due to the lack of semantic insight presented within these logs. First, system-level provenance logs do not describe the exact configuration fields that were updated during the attack. As a result, an analyst is not able to distinguish the authorized configuration updates from system administrators from the unauthorized code injection-based configuration update that resulted in the attack. Moreover, to make matters worse, in the case of in-memory attack on Redis, no events in the log describe the dynamic configuration change that led to the privilege escalation in that case. As a result, system logs in this case paint an incomplete picture of the attack. So to carry on with the investigation and in hopes to identify some more information, the analyst then turns to application event logs such as info debug messages in hopes to gain some additional context. However, unfortunately, neither Exponent CMS nor Redis creates any record of file-based or memory-based configuration changes. A survey on developers' logging practices reveals that developers typically do not take security factors into consideration while making these logging decisions, and that can explain why configuration change log events are not primarily found in application event logs. To further validate this observation, we surveyed 18 prevalent and widely used applications and found that none of these applications were creating any records of file-based or memory-based configuration change events, which renders application event logs ineffective when trying to investigate the class of configuration-based attacks. So keeping the challenges associated with existing techniques in mind, we set out to design a system, a provenance tracker, with the following design goals in mind. First, our system should have support for fine-grained detection of application state changes, such as configuration changes, regardless of the update mechanism, be it file-based or memory-based. Second, our provenance tracker should be able to correctly associate application state change events with the system events. For example, it should be able to attribute the change of a configuration to a specific process or a specific user. Lastly, our system should be able to efficiently audit the application state while also avoiding high runtime and storage overheads. So keeping these design goals in mind, in this work, we propose Dossier, a specialized provenance tracker that audits the application state and encodes the changes in application state information within the OS level audit logs. Our system supports the two main interfaces of application state changes, as discussed before, that is change of application state in memory or on disk. Moreover, while we are motivating our approach through configuration-based attacks, we note that our system, Dossier, is a generic tool for auditing any application state that is stored within program variables or within program files. So our system consists of two main components. The first component is responsible for memory-based tracking. In this component, the system administrator analyzes the application source code and provides annotations specifying the configuration variables that need to be tracked. Our system Dossier then uses these annotations along with the application source code and performs novel LLVM-based static analysis to identify all the sites within the program where these configuration variables are getting updated. Dossier can be configured to handle explicit flows as well as address-dependent implicit flows during its propagation, as shown in line 8 and line 11 respectively. Afterwards, our system applies different filtering techniques to rule out any false positives if need be. This can include logging only one update per basic block or logging updates within a specific function. Then, Dossier adds the instrumentation hooks within the program, and finally, these instrumented target applications have the capability to emit configuration-based change logs during runtime. So the second component of Dossier is responsible for file-based tracking. In this case, our system takes as input a list of configuration files that need to be tracked. It then loads a custom Linux kernel module, which intercepts any write-related system calls, such as write, pwrite, vwrite, etc. If that system call is writing to a configuration file, Dossier extracts the data buffer for that system call and logs the data buffer along with any metadata information such as PID, TID, etc. And lastly, the system call is returned back to the system call handler. So during our experiments, we observed that for certain applications, even if they're updating a small part of the file, they end up rewriting the complete file itself. For example, in the case of Exponent CMS, when the port within the configuration file is changed from 25 to 1505, the complete file is rewritten in 6 system calls. The first 3 system calls override the same data at the same offsets. The port gets updated in the 4th system call, and as a result, 2 bytes are added within the file, and these 2 bytes are then cascaded to the 5th and the 6th system calls respectively. So in this case, we made 2 observations that makes the file delta computation part not as straightforward as you might think. So the first thing that we observe is that you cannot compute the correct file delta by comparing 2 write system calls writing at the same file offsets. For example, in this case, if we were to compare chunk 1e with chunk 2e, that is like the 5th system call, we'll come to the incorrect conclusion that 2 bytes were added to the start of the chunk and 2 bytes were removed from the end of the chunk, and in reality, neither of these conclusions are true. Moreover, we also observed that we cannot compute the correct file delta by comparing the complete file state between 2 contiguous write system calls. For example, in this case, if we were to compare the complete file state between the 4th and the 5th system call, we'll again come to the incorrect conclusion that 2 bytes were added and removed from the file. So based on this, we observed that in order to compute the correct file delta, we need to compute the differences between the complete file state before the first system call and after the last system call during an update. And based on that, we propose a solution where we cluster different system calls together and compute accurate file deltas. And moreover, this also removes any unnecessary logs that are being collected due to complete file rewrites. And the details of our algorithm can also be found in the paper. So moving on, during the runtime phase, in addition to the system level audit logs, Dossier collects the memory-based configuration change logs from the instrumented applications, as well as the file-based configuration change logs from the Linux kernel module. Now, during the investigation phase, upon an indicator of compromise, Dossier combines the configuration change logs with the system logs in a causally correct manner in order to generate holistic provenance graphs, which then lead to effective attack reconstruction in the case of configuration-based attacks. So, to elaborate further on this, let us now go back to our initial case study, and now we'll see that how Dossier basically, how the scenario differs when our system is running on the compromised machine. So in the case of file-based attack on Exponent CMS, Dossier additionally logs the exact configuration fields that were updated during the attack, specifying the code injection in the third update. Moreover, in the case of file memory-based attack on Redis, Dossier extracts the exact configuration change events that led to the privilege escalation in that case. As a result, the holistic provenance graph generation aids attack reconstruction and provides better context while identifying root cause of the attack, which led to privilege escalation and which led to basically code injection. So to move on to evaluation, we evaluated our system both in terms of correctness and the runtime overhead. So for evaluating our file tracking module, we measured the time overhead for making write system calls with and without using our Linux kernel module. Our results show that system call interception leads to an average overhead of about 3%. Moreover, we observed that logging and processing configuration-based writes leads to an additional overhead of about 4%. However, we observed that the overhead associated with our file tracking module is inversely related to the percentage configuration writes. And as the percentage configuration writes decrease, the overhead associated with our system is essentially reduced to the overhead associated with system call interception. Moreover, we also evaluated our system on various micro benchmarks such as lmbench, postmark, blast, etc., and also only observed a maximum noticeable overhead of around 5%. And our system, Dossier, is able to achieve these low overhead numbers due to kernel integration and due to the use of inbuilt kernel logging functions. So moving on to evaluate our second component, that is the memory tracking component, we evaluated the correctness as well as the overhead of our basically tool against two popular open source applications that are Redis and Nginx Unit. In order to evaluate the correctness of our static analysis, we provided these applications different synthetic inputs and computed the correctness of our application instrumentation against manually annotated ground truth information. So our results reveal these informations. First, we saw that in most cases, the runtime overhead associated with application instrumentation is under 2%, with a maximum observable overhead of only 8%. Moreover, one of the observations that we saw was that when Dossier was configured to handle implicit flows, the precision associated with our analysis is reduced due to the introduction of false positives. However, we note that this is not a direct limitation of Dossier, but an inherent limitation of the underlying program analysis techniques that are being utilized by our system itself. And lastly, we argue that despite the inaccuracy with implicit flows, system administrators have the option to disable implicit flows at the cost of completeness and still get reasonable recall values with very high precision. So our system, Dossier, does suffer from some limitations. First, since our system builds on top of LLVM, due to open challenges associated with program analysis techniques, our system requires the source code of the application for static analysis and instrumentation. And lastly, it also requires some manual instrumentation from the system administrators for specifying the configuration files and the configuration variables that need to be tracked within the system. So to conclude, in this work, we proposed Dossier, a novel provenance tracker that is able to log application state and combine that with the OS level events for better attack reconstruction. Our system features a lightweight kernel module for file-based tracking and uses program annotation along with static analysis for memory-based tracking. Our evaluation on realistic workloads, as well as 5 different real-world attack case studies, shows that Dossier's generated provenance graphs are able to effectively reason about configuration-based attacks with minimal runtime overhead. So thank you so much for listening to my talk, and this is all from my end, and I'm open to any more questions.